Hello, good evening, everyone. I am audible, right? Hello.
Yes, ma'am.
Good evening, everyone. Welcome to the interactive section of the course System Design through Verilog, week 3. In the last week class, we discussed about the adder subtractor module. So, is this adder subtractor module like clear? Fine. Any doubts in this module? So, in this adder subtractor module, like when we are performing addition, say like all the four ones plus in this we will get 0, 1, 1. So carry will be 1. So when we are performing addition, we will be in this block only. So the carry out will be this C out. And this will be the results of the adder. And we will perform this operation only when the M is 1. So this circuit is clear. Any doubts in adder subtractor module? Proceed with the week 3. In the week 3, we will cover the decoder, encoder, multiplexer, demultiplexer, and some of the flip-flops and the version of modem. So the first circuit is decoder. So for a decoder, like let us start with a simple decoder. So this truth table is for which type of decoder? How many inputs and how many outputs? Yes, this is a 2 cross 4 decoder. So for writing the equations, we can directly write it from when output y0 is 1, whenever x1 is 0 and x2 is also 0. In the same way, y1 is 1 whenever x1 is 0 and x2. So this one. This is 1 when x1 is 1 and x2 is 0. So x1 x2 bar. So this is the equation for y2. And y3 is 1 when both are 1. So x1, x2. So for the logic to get this logic diagram, we will use this equation. So I need x1 and then I have x2. And then this one I one inverted version x1 bar and x2 bar. And my y0 is x1 bar and x2 bar. And my y1 is x1 bar, x2. My while C1 is one, right? So, so in this, I need the inverted version of x1 and x2. So this I am defining as w1 and this I am defining as w2. And then I'm defining this as gate g1, g2. So I'm obtaining the y1 as the inverted version of x1, and okay, this I in the diagram I have represented as x3, and the inverted version I am obtaining as w2. And then this is my gate g2. And my gate g3 I am performing the AND operation of w1 and w2. And then I am performing w1 and x2, this x of 0, and w2 and x1. So G4, G5, and then G6. And then X1 and X0. I'm getting the Y3. So is this 2 cross 4 decoder clear? Any doubts? Okay. So next is if we want to generate, we want a decoder with the enable signal. So if enable is 1, I will perform the normal encoder operation. If enable is 0, I want output to be 0. So for that, I will, as we are using AND gate, any one input to the AND gate, if it is like tied to 0, then the output will be 0. So I will use the same circuit, but now 3 input AND gate. Y2, Y1, Y0, 0, X1, Y, X0, X1, Y, X0, X1, X0, X1. So for this, I will connect a third input. Just the enable signal. If enable is 0, then all the outputs will be 0. If enable is 1, then we will have the normal operation. Okay. So this we are like with enable we can use design a larger and decoders using the smaller decoders. So the next is 3 cross 4 decoder using the 2 cross 4 decoder. Now we have designed the 2 cross 4 decoder. Now we will use the decoder with the enable signal. So if I am having a first decoder which is 2 cross 4 decoder and another 2 cross 4 decoder. So I will be getting the 4 outputs. For 3 cross 8, I need 3 inputs and 8 outputs. I have 8 outputs. For one more input, this will be the 2 inputs. For another input, I will be using this enable signal. So to this 2 inputs, what should be the input values? Trying, trying to map this to one decoder and this one to another decoder. So for this is like till this. So what should be the enable value? E0 or E1 I should type to. or else, okay, let us start with this input. So what value I should have here and here? I'm audible, right? Yes, yes, x0, x1. And to this, say first decoder, what should be this E0 value? This enable I have to type to, because I have used only two inputs, I need to give the third input. I have to select between this to get either this output or this output. Yes. So I will connect this if I'm giving like y0, y1, y2, y3. That time this is 0. So I will connect a NOT gate and then E and then E here. So that here I will get this when x, this is selected when x2 is 1. So we get y4, y5, y6, y7. x0, x1, x0, x1. So this is the 3 cross 8 decoder using two 2 cross 4 decoders. So for this we need a decoder with enable signal. So for enable, for every AND gate operation I have to perform with enable signal also. So first you can see all the 4 outputs we have to AND with enable signal, and enable will be one of the input. Now we will use this 2 cross 4 decoder with enable signal for this, for designing the 3 cross 4, 3 cross 8 decoder. So first I am instantiating the decoder once. So this decoder where my inputs are x1, x0, and this enable is my wire, and I have defined the NOT of the enable. So here the normal E and here E bar, which is something but x of 2. Like x of 2 and here x of 2 comp2. And then the second decoder I am instantiating here. Here I am getting output from y0 down to y3. And here y4 down to y7. And my inputs are x1 and x0. And my enable signal is x of 2. So is this like code clear? The Verilog code for 3 cross 8 decoder using 2 cross 4 decoder. Any doubts? Yes. Next, the next circuit is encoder. So the encoder we will, okay, this is with how many inputs and how many outputs? This encoder,
8 outputs.
8 outputs or inputs?
Inputs, 8 inputs, 3 outputs.
Yes. So
8 inputs, 3 outputs, ma'am.
yes, it is 8 cross 3 encoder. So x0 till x7 are the inputs and y0 to y2 is the output. So this also we will write the equation like y0 is 1 when x1 is 1, when x3 is 1, when x5 is 1, and when x7 is 1. So same y0 I will get an x1, x, x1, x3, x5 and x7. x3, x5 and x7. And then the next y1 is 1 when
X4, X3,
um, yes x2,
X3 man, X3, X4,
yes x3, x4, this is x3, this is x2, and then here, so this is x6,
X6, X7,
x7, and then x2. And then y2 is 1 when it is from this 4 to till 7. So y2 is 1 from x7. So now this logic diagram we need a OR operation y2. If I want to define, I need 4 inputs x4, 5, 6 and then 7, and to generate y1,
X2, X3,
x2,
X3,
x3, 6, 7. Yes. And then to generate y0, we need x1, x3, x5 and then x7. So now the same thing we will implement in the Verilog output. So now we need 4 input OR gates. So to first to we will okay directly this equation we can implement. So first I am for getting y2 we need to from 4 down to 7. I can directly pass. For y1 I need to pass x2, x3, x4, x7. So if I am taking it as like this as a register type, I will use this operator and then I will pass all the inputs inside. This is called the concatenation operation. And in same way for y0, I need x1, x3, x5 and x7. So and to implement the 4 input OR gate, I will be like first implementing this, storing this like this will be a wire type, again third input, again the fourth input. So I need 2 wires, W1, W2. This will be the 4 inputs and then output. In priority encoder, so in the previous encoder, like if we have only one bit will be set to 1, any one of the input is assumed to be 1 and then we write the code. But in priority encoder, more than one inputs can be 1 and we will assign the priority to it. So this is again the same 4 cross 2 encoder with uh, enabled signal, like this represents the valid Okay, this is also one of the like output. So if I have all zeros, this is an invalid sequence, and the output will be it will be don't care. Now, if I will assign a priority, so this will have like highest priority, and this will have the lowest priority. So if this and this are 1, so I will give priority to this and I will encode to x1. And in the same way, if this bit is set 1, I will give no priority to this x2 and I will encode it as x2. The same way for x3, again I will set it to x3 and I will encode to s3. And like this table further will continue. And all the encodings will be like giving priority to 3. Okay. So this is the priority encoded truth table. And now multiplexer. Till here everything is clear. Like any doubts? Encoder, decoders. Okay. So here now we will start with the multiplexer. Now this multiplexer is having how many inputs and how many outputs?
One output. S0, S for input.
Yes. So this is a 2x1 multiplexer. And so the Y equation, output equation will be Y is selecting I0 when both S0 and S1 are 0, plus it will select I1 when S0 is 1 and S1 is 0, plus it will select S2 I2 when S1 is 1 and S0 is 0, plus it will select I3 when both S1 and S0 are 1. Okay, so this one where we are discussing, sorry, this is 4 cross 2, 2 select lines. So here we will write 2 to the power n cross 1 multiplexer, and n is the select line. So this is a 4 cross 1 max. Sorry for the confusion. For 2 cross 1, we will have 1 select line and 2 inputs and 1 output. So multiplexer will have always 1 output and 2 to the power n we will be representing as mux, and where n is the number of select line. So this is the select lines are 2, S1, S0, and there will be 4 inputs which will connect I0, I1, I2 and I3, the final output. So this is a 4 cross 1 mux. And now applications. So now we will implement this equation as a circuit diagram. So first I will select I0 when both S0 bar and S1 bar. I will be selecting I1 when S0 and S1 bar. And then the next will be I2 when S0 and S1, and then I will select I3, then S0 and S1 both are, and the final output I will pass through a OR gate. So here we made 3 input AND gate and a 4 input OR gate. So first I have to obtain the S1 and S0 bar. So I will store in W1 and W2, and then this output I have to store it in a wire. So I will store them as P0, P1, P2, and then P3. And then I will apply through a OR gate and obtain the final result. So this we need one 4 input OR gate and 3 input AND gate. So 3 input AND gate also we have to write, like, define this module. This will be our AND 3 and OR 4, like how we saw in the previous slide. This will be our OR 4. Any doubts in this 4x1 multiplexer? This is a 4x1 multiplexer using basic gates. So next is,
Ma'am,
yes,
uh, for 16 into 1, how can we write that code, madam? Is it with logic gates or is there any simple way?
uh, that, like, we can directly code in the behavioral coding, where we can directly define this truth table itself as a in the code, or else in
Yeah,
if else statements, those things you can use it.
yeah, okay, ma'am.
Or if you get the equation, this equation directly you can write like this: assign I0 and S0 bar as a one line equation. Instead of instantiating each gate, you can directly assign this in an equation. And 3 and as well as this OR 4 are not inbuilt primitives. These are user defined modules. So we have to write the Verilog code for them and the 3 and OR 4. Any other doubts? The next is, okay, first we will define this 4x1 multiplexer, and then we will instantiate this to obtain the higher like 4x1 multiplexer using the 2x1 multiplexer. So here I have like one select line, and we need I0, I1, two inputs, one select line, and Y. And here these are also inputs. So we have uh, like 4 inputs, 2 select lines, and 1 output. So for this, we will be having 2 input, 1 select line, and 1 output. Okay. So this one, truth table, if you see, I will, if it is 0, I will be selecting I0, 0, 1, and 1, I will be selecting I1. and the equation will be y is equal to S0 means I0 plus S means I1, and then I will need S signal, and then S0 S complement. When S is 0, will be selecting I0, and then S is 1, I will be selecting I1. So this one we have to pass through all it, and then the final output. And so this code we are using basic kits, like completely defining with the basic kits. So first we need S complement and storing it in our W1, and then performing AND operation between W1 and I0 and storing it in W2, and then performing S and I1 and then storing it in W3, W2, W3 OR operation storing it in Y. So this is our code for 2x1 mux. Now the same 2x1 mux we can implement using a buffer. So if I have a buffer like this, say this is C, this is X, and this is Y. If C is equal to, say I'm using normal, I have not kept any bubble here. So if C is equal to 0, then Y will be, and this buffer circuit, if I am having X here and Y here, if my this input is 0, then what will be the Y? Yes, it will be high impedance too. And when C is 1, it will be X. It is like this X, not don't care. So I write X one side. This is this X. So now we will use this buffer to obtain this 2x1 multiplexer. So first I need a select line. So I will pass this as a select line. And first here I need S is equal to 0. That time I will be selecting I0. And then another buffer. Here when S is 1, I will be selecting I1. So I have to, of course, if the select line is 0, then this node will be floating. So I can directly connect it, and then I will obtain the final output Y. And so this we will implement without bubble. We are having this is buff if 1 is the keyword primitive name, and then the output is Y, I0, and I am storing I1 complement, this S complement, and this W. So I will have I0W is Y, and then I1 S is again Y. So I have shortened and end module. This is the 2x1 multiplexer using the buffer. And then now we can instantiate this multiplexer to design a 4x1 multiplexer. For a 4x1 multiplexer using a 2x1 multiplexer, how many inputs, like how many times I have to instantiate the 2x1 multiplexer? Yes, 3 times. So this will be truth table, and I will have first multiplexer 2x1 multiplexer. I will apply 2x1 multiplexer. This will have one select line and two inputs. So if I have S0, you can see it is till this portion. Okay. When S0, if it is 0, it will be getting I1. When S0 is 1, it will be I0, I1. I will get one output, I will store it in some wire. Okay. Then again S0, when it is 0, I am selecting I2 and I3 when it is 1. Now I have to apply this to another multiplexer and the select line to close one. So when it is 0, you can see this is 0. I'm selecting I0 and I1. Okay. So when S1 is 0, I will be selecting this portion, this output will come. And S1 is 1, I have to choose between I2 and I3. This multiplexer will be selected, and based on S0, I can either get I2 or I3. So this one we need one output, four select inputs, one output, four inputs, and two select lines, and two wires. One for this multiplexer, first multiplexer output, and another for the second multiplexer output. First multiplexer inputs are I0, I1, select line is S0. Second multiplexer I of 2, I of 3, and then S0. And then the third multiplexer output is Y, input is W1, W2, and the select line is S of 1. So this is a 4x1 multiplexer using 2x1 multiplexer. Okay. So if instead of like using the basic gates and instantiating the multiplexer, I can also derive this multiplexer using the buffer circuit. So okay, so this is the implementation of 4x1 multiplexer using buffer. How many buffers I need? Okay, first we'll start like this. Let us have, I have two inputs S0 and S1. These are the select lines. And if I have some circuit which will give me four outputs to select, like if it is 0, 0, this line should be selected or this line should be selected, so that I can proceed for further circuit. So this S0, S1 and this circuit. What is the circuit that will give me the like this output? Like it will take S0, S1 as the input and give me Y0, Y1, Y2 and Y3. Yes, it is a decoder. So I need a 2x4 decoder. And now this will be selected. If this is selected, I need I0 to be the output. And for example, if this is getting selected, then I need I1 has the output. And then if I'm selecting this Y3, then I need I2 as the output. And if it is selecting Y3, my output will be I3. So I can short all these buffer outputs because at any one instant, any one buffer will be conducting and other will be in high impedance state. So This is our logic diagram for 4x1 multiplexer using the buffer circuit and one decoder. Is this clear? Any doubts till here? Okay. Then next we will be using our 4x1 multiplexer to design our 8x1 multiplexer. So for 8x1, how many inputs I need, how many select lines, and how many output. And the given is 4x1. So for 4x1, how many input, select line, and output are available. So for 8x1 multiplexer, how many inputs I need? Okay, 8 inputs, 3 select lines, and 1 output. Yes. And for this, we need 4 input, 2 select lines, 1 output. That is, this will be 2 to the power n, and this will be n, and this will be always 1. So, how many multiplexers are required? How many 4x1 multiplexers are required for one 8x1 multiplexer? Yes.
Two 4x1 multiplexers and one 2x1 multiplexer has required.
Yes, yes. So, first I will use one 4x1 multiplexer. So, I need to select lines. S1, S0. So, last two, I will be having I3, I2, I1, I0. Again, when S3 is 1, this S0 and S1 will be having all the 4 combination. So again S1, S0. So this will be having 4 combinations. So this time I will be selecting I4, I5, I6, I7, and now I have to select between this and this. Like, so this, the truth table of C till this. Here again you will be having the same 4 combinations. So this one we are obtaining in the first stage. Now to select between the first multiplexer and the second multiplexer, I need another 2x1 multiplexer, and I will apply this S2. So I will get the final output. This is 4x1, 4x1, and 2x1. So for 2x1, number of input will be 2, select lines.
One output.
Yes. So this is clear. Any doubts? Any doubts in this multiplexer? Will So the next circuit we will proceed with. We will start a multiplexer. So it will be having 1 cross 2 to the power n. The notation is 1 cross 2 to the power n. So for n select lines, we will have 2 to the power n output, and the input will be I0. This I0 will be available at one of the output line which will be selected based on this select line and S1 or S0. So this circuit is similar to answer is here itself. Okay. The name of the circuit which will select any one particular output line based on the given select lines. Say if 0, 0 is the input, say I'm having say some T1, T2, then O0, O1, O2, O3. This will be the output. So the circuit, the name of this circuit is, or say 0, 1, it will be like. Can you name this circuit? I'm giving the input combination like 0, 1. It is selecting this line and it is rectified. Yes, this is a decoder circuit. So same 1 cross 4 demultiplexer is similar to 2 cross 4 demultiplexer if we exchange the input with the select lines. So here we need 2 inputs and here we will have 2 select lines. Okay. So next we will proceed with the flip-flops. Any doubts till this? Till now we have discussed all the combinational circuits. Any doubts in decoder? Okay. Okay, then we can proceed. Our first flip-flop is S bar R bar latch. So I'm saying it latch because I'm not using any clock and also it is either sensitive to the level or I'm not using any clock. So first circuit I will like first let me do the circuit. Okay, this is Q. And this input is S bar, another NAND gate bar. So I will short this. This will be Q bar. Yes, any doubts? Okay. So first let me start with 0 1 combination. If S is 0, S bar is 1. R bar is 0. If the gate is NAND gate, can you say if I write the NAND gate truth table 0 0 0 1 1 0 1 1, for this combination it will be 0, for other combination it will be 1. So I know the output. When one input is 0, the output is fixed to 1. Then what will be the value of Q? Yes. So here I will get 1 and this combination 1 1 will be 0. So we get the output 0. Same way next. If we have 1, 1 means the S bar will be 0 and R means R bar will be 1. Any one input is 0, I will get 1. I will get 1 here. Q bar will be 0. Okay. And now if I have say 0, 0 state, it will be like retaining the previous state. 0, 0 can either be, sorry, not 0, 0, 0, S bar, S is 0, R is 0, so S bar is 1, R bar is 1. In 1, 1 state, if you say, if any one input is 1, it can either be 0 or 1. So it will retain the previous state. And if it is like 1, 1, this state is 1, 1 means S bar is 0, R bar is 0. If both are 0, any one input tied to 0, output is 1. So both Q and Q bar cannot be same, so this state is not allowed state. And the Verilog code, we need 2 NAND gates, and one of the input is SB, and I have the QB. Output is Q. Here RB, and the output is QB and Q. Okay. Any doubt in the S bar R bar latch? Any doubts? Yes. Here I have written S and R. While mapping, I am mapping as S bar and R bar. If I write directly S bar R bar, then it will be different. Like when I say it is 0, 1, I am writing it as 1, 0. When 1, 0, I am taking it as 0, 1. Here when I am in SR latch, we will write the truth table again. Here 0, 1, 1, 0, 1, 1. So when S bar is 0, R bar is 0, any one state is 0, then the output is tied to 1. So this is like not allowed state. When S is 0 and R is 1, the state is 0. So I know the output. This will be always 1, and this 1, 1 will come here, so it will be 0. So output will be 1. When it is like 1, 0, this is 0, so I know this will be 1 and this will be 0. So I will get 0. If it is 1, 1, it can be like the previous one. So it will be like memory. So it will be the same previous state QI. So this will be the yes, both are different. S bar R bar, this will be the truth table, and for SR length, this will be the truth table. Or while when you are taking, just You okay, if you want to check what will be the output for when S is 1, R is 1, while taking I was considering as 0 0, and when it is 0 0 I am getting the not allowed state. For 0 0 it is invalid, and 1 1 it shows previous state. Yes, for 0 0 it is not valid, and 1 1 it shows previous state. And when it is 0 and when set is 0, S bar is 1, so this is set to 1. When it is reset is 0, reset R bar is 1, so it is reset to 0. Now it is time for any doubts. Okay. So next, now we will come to the SR lens. So here again, we will be having the same circuit Q and then QB, QB, Q. And here I will have SB, RB. Now I need to complement this, like how when I was considering from this truth table, I was like just complementing and taking the S and R values. The same way in the circuit also I will be just complementing the S value and R value. So I will get the SR latch. So this portion is my previous S bar R latch, and this I have to obtain this two wire value. So my SB and RB are the two wires. SB is the two input of the NAT gate I am tying to S signal and obtaining the SB, and the same way two signals I am tying to R and obtaining the RB signal. Then I have to instantiate this same SB RB latch module. So SB RB latch I am instantiating. The inputs are SB RB and outputs are Q and QB. And now here the same, this will be the truth table. Because I have taken the complement, so I can directly take. So, okay, first let us take like 1 and 1. If both the inputs are 1, this will be 0, this will be 0, and output will be 1. So this is not allowed state. Any doubts? So is the code for the SR latch and S bar R bar latch clear? Yes, yes, please. You can ask.
Ma'am, here we don't have any enable, right? So how we can say it's a latch?
Latches, it is like either level sensitive or it is like some delay block. Flip flop, we need it should be, if it is sensitive at the edge, this edge sensitive devices we will call as flip flop. So
Yes.
either if it is a level or this one, if there is no enable, it will be sensitive to both positive and negative level. So this is also one type of latch.
Yes. Yes. Okay. Understood.
The next,
And then, ma'am, we can't
yes,
say it's a synchronous circuit, right?
this one.
Yeah, this SR latch is a asynchronous circuit, right?
I have not used any clock here. If I say it is a synchronous circuit, then they complete, like if I say there are some 4 modules, all these 4 modules will be operated by the same clock. But if it is asynchronous, like this output may act like the input to this output may act like the input to this, and I will have one clock. So like this circuit we will call as asynchronous. So as of now, like this is just one latch. How it will be operated, based on that only we will be able to say like whether it is asynchronous or synchronous.
Actually, in the assignment, we got one question related to that. Like it's a same diagram we need to build, and then they are asking for it's a synchronous latch or asynchronous latch.
So deadline for the assignment is completed.
No, actually, tomorrow is the last day.
Then maybe we can discuss that circuit in the next week lecture.
Um, yeah. Okay.
Yes. This
Okay, ma'am.
is like
Thank you.
I am giving some generic explanation for the synchronous and asynchronous circuit without any specific to this or any other circuit. Because before the
Okay, ma'am.
deadline we cannot discuss assignment questions, right? So this is just a generic definition. So if I say it is a ripple counter, this output is applied to this clock and this output is applied to this clock, then this ripple counter we call as asynchronous circuit. And if all are operated by the same clock, then we call it as a synchronous circuit.
Ma'am, can you please here connect S1 input and R input to enable? Here, here NAND gate we have, right? We use it right here.
Here you are saying to tie to an enable signal.
Ah, yes, 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 yes.
Yes, that will be yes, like positive level latch or negative level latch.
Okay, so we can't say it's a synchronous.
No, that I will not say in this lecture. Like,
Actually, a little bit complicated.
yes, because it is assignment question, so maybe next lecture we will next Tuesday class we can discuss.
Yeah, sure, ma'am. Thank you.
Yes, latch is a sequential circuit. Yes, latch is a sequential element. Latch and flip flop. So sequential element is something which is having memory, and here I am having feedback, so I can have a memory. So it is also a sequential circuit. Any other doubts? So like how you said, if I have one enable signal, I will be having the same circuit. Now this will be sensitive to the level of the clock. I will have one enable signal and S R. So this will be again this is the R B Q Q bar. This is the circuit, right? You were saying. Here we will have an enable. So now it will be sensitive to this level. And now for this, I will be instantiating this module. So I will have input SBRB, output Q1, Q1. And then I need two NAND gates. One input will be S and another will be clock, R and clock. So like here I have defined as clock. So this is like clock. So this is will be sensitive to this level. So is this circuit, this code fine? Any doubts? The next code is we will have D latch. D means delay latch. So in this circuit, if I have 0 0, then what will be the Q and Q bar? Q bar, say n plus 1. Next state, what will be the Q n plus 1 and Q bar n plus 1? In this circuit, if say I am in the positive level itself, what will be the Q n plus 1 and Q bar n plus 1? Yes, it will be previous state. So Q n bar. So if I can tie both, if I am having S as 0, R has 1, I am getting the output as S. If I am having S as 1 and R as 0, I am getting the output as 1. So if I tie both 0 0, I will get the previous state, but 1 1 I will be having not allowed state. So for example, if I can have R has the complement value, then I will get the same whatever is there in the S, I will be getting in the output with 1 clock cycle delay. So with this I can get build one D latch. So is this fine? How we are going to like convert an SR latch to a D latch? So let me first have the same S bar R bar latch first. And then here I was having S, and then here I was having R. This two I was like tying, and I was having enable signature. What should be S and what should be R? Say if I have D as the input. If I give S and R as B, if it is 0 0, I will retain the previous state. But if S and R are say 1 1, I will reach the not allowed state. So I cannot tie to 0 0. If it is 1 1, then I will be in not allowed state. Yes. So here I will apply the D directly. I will take the not complement and apply to this. So same how I explained here. If what S is complemented in version here in the R, and if S and R are in complementary version, then whatever is the S we obtain at the next state of the Q1 with 1 clock cycle delay. So for that, so S should be D and R should be D complement. So this is our D latch, which is sensitive to enable. So it is positive level triggered D latch. And now I need a one NOT gate. So I will have this as DD. And then these two are enable signals. I will get SB here, RB here. In this portion, I can directly instantiate QB. Instantiate my SB, RB latch. Any doubts in this deluxe? This I have instantiated here, and this to obtain this BRB. Yes, both enable and clock are same. Like usually we say enable when say like enable is equal to 0 or enable is equal to 1. In clock we can have everything like either 0, 1, pause edge and neck edge. So enable, if I say enable is equal to 0, I am meaning to say that it is the 0 level in the clock. If I say enable equal to 1, I am like trying to say this level in the clock. And when it comes this, we will be calling it as like process. This we will call as package. Yes. The next we will design the flip flop. So D flip flop, okay. Either we can have master slave combination for the D flip flop, or the one of the positive level triggered D flip flop, some optimized version where just we need 6 NAND gates is given in this book, and the circuit is I have same one R bar S bar latch, the S bar R bar latch. Here we need 3 input NAND gate, 1 more 2 input NAND gate. We have the input. Here say we are having P. This input we are tying to this. And this one we will tie to clock. This version we will tie here. So say this one we will say 1, second instantiation, third instantiation. As like this here, okay, some differences there. This is third instantiation, second instantiation. So this one code, if I am trying to explain, is SP is one of the input, and the other input is CP. The output is S. So this will be S and SB. And if I am instantiating this one, this I have 3 input NAND gate. So I will have one more module definition. So one input is this one, SB. The other input is P, which output is R and P. Input is SB and another input is D and another input is CP. And this is the third. This is SB, RB are input. Q is one in output, QB is another. So for this circuit explanation, maybe you can try referring to this book. If you have any doubts in the circuit explanation, maybe we can discuss in the next class, next Tuesday. So this code, is it clear? If I'm not, 4 NAND gates are enough to build the flip-flop, right? I think this is one of the optimized version they have given in this book. The another version will be, we need this circuit D4 and another 4 at the slave stage. So maybe I need 8 and plus some inverters, if I'm not wrong. I will be having same for the master stage, same this circuit for the slave stage. I will apply one clock here and the negative of that clock here. Then this will be the flip-flop. So here I have some 4 NAND, here also some 4 NAND. It will be more than like 4 plus 4, 8. Is your doubt cleared? If we use some normal combination like without that optimization version, using the master slave, we can build this D flip-flop using the D latch.
Yes, sir. Yes, ma'am.
Yes, so this is the optimized version. The next question is, what will be the main difference between the latch and the flip-flop? Yes. So if I say latch, I mean to say it will be sensitive. It will be like transparent at either this negative level or positive level, or it will be sensitive to both the levels. So it is level sensitive. And if I'm saying it as a flip-flop, either it will be transparent and sensitive at the positive level or negative level. So flip-flops are edge sensitive. Is this clear? Any doubts? So now here we have this SBRB modules we have discussed earlier. But now we need SBRB FF1 where we need one NAND gate to be 3 input NAND gate. So can you say if I want to define 3 input like NAND gate, what will be my circuit? Say I'm saying NAND 3. So this NAND gate, I say AB. If I directly connect, say, another NAND gate and C. So this is how we used to do when we were implementing a 3 input AND gate or 4 input OR gate. So will I get here A, B, C bar? Will I get the NAND of A, B, C? Is this 2 NAND gate sufficient for me to design a say 3 input NAND gate? No, this. So here because I will get A, B bar, and if I come here, then again I will get A, B will have a bar and the whole bar. So I will not get the NAND of A, B. So we need to complement this again to get back A and B, and then again perform a NAND operation so that now we can get A, B, C, and. Okay. So this is our 3 input NAND gate. So we need X and Y, X, Y, NAND operation. I'm getting W1. Okay. Then again I am applying this to the 2 times and I am getting W2. And then I am applying this W2 to Z. I'm getting the final NAND output. So this is my 3 input NAND gate implementation. And here I have one 3 input NAND. So in the circuit, if you see, here I have one 3 input NAND. Where I need one SB clock and this QP. So I have to pass SB, QB and Q and then temp and then SB, RB, Q. So this is module I have implemented and I will instantiate here. So till here, any doubts? Now next we will proceed with the assignment question. Any doubts? Yes. So now this is the first assignment, previous year first assignment question number 1. Yes, so you can see some gates here. Let me try drawing the logic diagram. I have A. They have given if I perform NOT gate, I will store it in F. The next they have given B. If I perform the NOT operation, I will store it in G. Same way H. C. Okay. So now I have one AND gate and output is D of 0, whose input are F0, G, H. The other AND NAND gate is D of 1 and my inputs are F and then B and then H. And then my third thing D of 2, it is A and then G and then H. And then third one D of 3. So I have A, B and then H. So with this circuit diagram, can you identify which type of circuit is this?
I think it's answer B, madam.
B. So okay, now if we can write the equation, maybe we can get somewhat clear picture. I'm saying F A bar, B is B bar, C bar, and D1 is F is A bar, B, C bar, D of 3, 2 is A, B bar, C bar, D of 3 is A, B, C bar. So this is when it is 0, 0, 0, I am choosing this. When it is 0, 1, 0, I am choosing this one. When it is 1, 0, 0, I am choosing this one. And when it is 1, 1, 0, I am choosing this one. So you can see there are two options, whether we have enable or whether there is no enable. So if I say this has A, B and C, can you say which one is enable signal?
H.
Yes, C is the enable signal. C means like C bar, which is H is the enable signal here. And then the other, you can see the 4 combination here. 00011011. So it is, and you can see the final output I'm giving it to D0. So it will be like, say if I say 0, enable is 0. I'm enabling it. H is 1. And then I'm giving 1. So 0, 1 means I will get 1 here. So because of this, it is a positive logic with enable signal. So the answer is B.
Ma'am,
Yes, yes.
for negative logic, we have to use NAND gate, right?
Yes, yes. If you use
Yes.
NAND gate, then the output you will be getting 0. 0
Okay, ma'am.
will be for negative logic. And then this is another question. So has you asked, if I replace this AND gates with say NAND gate, then the code will be representing. We have already seen enable will is there because enable bit is H, and like as we have seen, it is a negative logic, so it should be D. Any doubts? So any Verilog code, if you have, if you can like write the equation and draw the like diagram and try mapping, you can identify which type of the circuit is implemented in this Verilog code. Why is enable always 0? Sorry, I didn't get your question.
Ma'am, here every time we are assigning, we are giving zero logic to AND gate, right?
Yes, yes.
So if whatever the value of A and B, the output will become for everything it will become zero, right?
No, here we have applied H only, right? When enable is 0, the H is 1, H is acting like an enable signal. So we will
Yeah.
be getting based on this.
Yeah. Sorry. Yeah, I got it.
And then the next question. So if I have another, like, say, again I will draw one circuit. For this one, it is C. I'm getting P. Let me write the equations first. My Y is nothing but P. Q. Q is nothing but P. P is C bar A plus R. R is B C. So this is the equation we will get for the output Y. So from this, can you say which type of the circuit is implemented in this Verilog code?
Ma'am, how did you write that equation, madam? Explain.
Yes. I have like my C is P bar. Sorry, P is C bar. This one will be output and this will be input. Always we will have output followed by input. So this will be output and this will be our inputs. So the same way I will have Q as P. P is C bar A and R is B C. Now I am applying the Y, which is Q, this one C plus CA plus BC.
Yeah, okay, madam.
So now we can get, I'm having C0, it is selecting A when it is 0. When it is 1, it is selecting my B input. So C is the select line, A is 0th input and B is the 1 input. So it is here this cross is missing. It is 2 cross 1 multiplexer with C as the select line. So C will be the option. Yes, correct. And then this is the next question. I have one NAND gate whose output is P. Okay. A is one of the input and Q is another input. A and these are inputs. This will be the input, this is the output. If I take like that, and then Q will be the output, P will be one of the input and V will be one of the input. So P is this one and Q is this one. So this one is our S bar R bar latch. So in this circuit, the question is like if A is 1 and B is 1, then after the execution, what will be the steady state values? Is this clear, like which type of circuit it is? A. Okay. Any other answers?
It's a multiplexer.
This question I have used two NAND gates. So if I like try to draw the logic diagram for this two NAND gate Verilog code, I will obtain this one. This. I will obtain this as a circuit diagram. Is this clear? This will be my final output circuit diagram for this two NAND gate implementation.
Yes.
So which type of circuit it is?
Sequential, right?
Latch.
Yes, it is sequential. Name of the circuit?
NAND latch.
Yes, so it is S bar R bar latch. So in that circuit, if I have 1, yes, if I have any one of the input, if it is 1, whatever the other input is, it can either be 0 or it can be 1 based on the other input. So I will be able to retain the previous state.
Ma'am,
Yes.
how can you say that it is S bar R bar latch, ma'am? Is there any difference between S bar R bar and SR latch?
Yes. It's just one convention, and S and R, you will be having the complement version and you will be applying to this SR latch. So in this normal S bar R bar, if I give 0, then I will be having not allowed state. But if I complement and give this here, if I give 0, I will get 1 has S bar R bar and I will be having the previous state.
Ma'am, both latch has the same truth table, right?
You will have the complementary version, like 0 is not allowed in S bar R bar, 1 is not allowed in SR. If I have 1 here, it is reset. It will be reset to 0. If it is S is 1, this set input, reset input. If S is 1, the output will be set to 1. But it will be in complementary way. If reset is 0, then I will have 1. If reset is 0, then I will be reset to 0. If set is 0, I will be having set to 1. And 1 will be opposite, not allowed. 0 will be previous state, 1 will be previous state. this slide, this complement alone will be the difference in the truth table also.
Yeah, okay, ma'am.
Yes. So this is S bar R bar latch, and I am having 1 as the input. So you can see if it is 1, the output can either be 0 or 1 based on the other input. So I can have this as the Pn. If I say Pn plus 1, Qn plus 1, I will have Qn. So I will be able to retain the previous state. So option D is the answer. The fifth question. In the code, if the same code, if I have A is equal to 0, A is equal to 1, B is equal to 0 before the execution of, after the execution of the steady state P and Q will be. If I have A is equal to 1, B is equal to 0, then what will be the P and Q values? Say I have A has 1 and B has 0. Option B. This P is equal to 0 and Q is equal to 1. Let us try it. I have one input 0. If any one of the input is fixed to 0, whatever the other input is, the output will be 1. So this is 0, so this will be 1. And I will get 1 here, 1, 1, I will get 0. So my P is 0 and Q is 1. Yes, P is 0, Q is 1. Option B is the correct answer. Any doubts still here? Like we have covered the decoder, encoder, multiplexer, demultiplexer, and SR latch, D latch, D flip flop in the Verilog code and the in the circuit. Any doubts? Any questions? Any clarifications? Yes, yes. Any doubts? Yes, encoder and decoder. So the first, like the decoder, the two inputs in the decoder part, like if I have x1 and x2 are the inputs, then I will be decoding this binary value and selecting one of the outputs. So if it is 0, 0, I will be selecting y1. If it is 0, 1, I will be selecting y1. If it is 1, 0, I will be selecting y2. And 1, 1, I will be selecting y3. So we are decoding the binary into the and selecting one of the output line. So we need AND gates, and based on, like say if I have this y1 has 1, so I will select y1 when x1 and x2 are both zeros. I will select y1 when x1 is 0 and x2 is 1. I will select y2 when x1 is 1 and x2 is 0. I will select y3 when x1 and x2 are both 1. So this is the operation of decoder. Any doubts in decoder? For the encoder, it is this is enable, and then this is encoder. So encoder, it is like opposite. Now I am selecting x1. So this I have to convert to the binary. It is selecting the x0 line. If it is x0 line is active, my binary encoded value will be 3 zeros. If it is selecting x1, my binary equivalent will be 001. If I am selecting x2, 010. Same way, say like x6 is alone active, then I will get 110. So in the normal encoder, I am considering like any one of the input line is alone active at a time, and then I'm encoding it. Whereas in the priority encoder, I can like have say x1 is also active, x2 is also active. In that time, I will be assigning high priority from this order. This will be having more priority. If this is active, then whatever whether x2, x1, and x0 are active or inactive, my final output will be encoded as this is x3, so 1, 1. And this enable E will represent whether this sequence is a valid sequence or an invalid sequence. So if say all are 0, the encoder means I need any one line to be active. So I am not selecting any line. So that time whatever the output is showing, it is an invalid pattern. It will be represented by the E. Any doubts? Yes, priority gates. Now you can maybe write the truth table for this, and then you can implement it. So, say same way, if I have y0, it is 1 when this is 1, and if y0 is 1 when this and this is 1, same way both are 1, the same way you can like proceed writing the equation, and then you can implement in the gate level. So implementing the priority encoder using gates, you can either like write the equations based on this. So now y1 is 1 from here, so you can get one equation, right? Maybe this is like 4 variable k map, and you can minimize it. Or if you are using like if else statement, you can say if x1 equal to 1 without any condition, you can directly assign the final output value. The same way like x2 without checking the other condition. So this way you can maybe generate the priority encoder code. Okay. What is the difference between the latch with enable and without enable? So latch with enable signal will be active at any one of the levels. So now if you see this, if whenever the input changes, you will find the output change. So it will be, it won't, it is not like any controlled signal. So if I say I have 0, 0, then I can see particular output. This may have some gate delay. Similarly, if I have 1, 0, I can see the output. But if I introduce an enable signal, then only when this enable is say 1, I will be able to see the output. If enable is 0, then we know the output will be like this, will be in the storage state. So whenever it is 1, that time only I will be able to, this S will be transparent and transfer to the queue. The latch will be transparent. Any doubts? I think synchronous and asynchronous latch It is one of your assignment questions. So maybe we can try this. We will discuss it in the next Tuesday class. Real-time example for encoder, decoder. So here also we have used one decoder circuit to obtain the value of y. If you say what this encoder, so okay, I will for saying any like for a real-time application of an priority encoder. You know about flash ADCs? If I have say any input voltage, say 0.7 volt, that it will be converting it to levels. So say if I have say n bit ADC, say 2 bits, I will have 4 levels, and this one, so it will be like deducting like say first comparator, second, third, fourth. So this one, it's like having threshold say 1.1, 0.1, 0.1, 0.2, 0.3, 0.4. So my voltage, so this points, say let me take 0.3 volt. This is greater than 0.1, so it will be 1. Greater than 0.3 or equal, yes. Greater than 0.4, no. So I will get the output as 0, 1, 1, 1. So now I have to encode this 0 triple 1. That time I can use this priority encoder like 0, triple 1. The output is after applying through the encoder, I can get the output as 1, 0. Any other doubts? Practical example that differentiates the use of latch and flip-flops. Generally, we will not be using that much latches in the design, because if I say latch, there will be a problem of race around condition. Say if I have in this as a clock correct, in this cycle, if it is this, it's very much higher than the delay. So within this period itself, the output may be changing. Like here, the output is Q is equal to say 1, 0. After some delay, it will be changing it to Q equal to 1. The gate delays are very less, so it will be usually in say picosecond. So if this delay is like this much alone is my clock. If it is like this my clock, then I won't have the race around condition. Otherwise, I will be having the race condition. So that thing, so this is the problem with the latcher. So we will be generally using the flip-flops in the design. So flip-flops, like if you say like practical examples, if I have say one adder block, I am applying this flip-flop. I have another adder. So this flip-flops we will be having here. So now my delay will be this much only, this adder block, and based on the setup and hold, the setup time of this and C2Q. But so to reduce the delay and like pipelining, those places we will be using this flip-flops. And latches, the application of latches are mainly in like say I have this flip-flop operating in one frequency. I have another flip-flop operating in another frequency. So mainly during the testing application, we may add some lockup latches or something to, in those places only latches will be used. Generally for designing, we won't be using latches because of this race conditions. So if I have this in one, have you heard about like scan chains? Okay, so if I want to test this circuit, for me this adder, any other block pins won't be available to the external. So I have this flip-flop. If I have this flip-flop, if I can apply any input and also see any output, I can test this adder block. For testing purpose, I will be connecting this flip-flop in a chain fashion, and I will be adding some multiplexer logic to like enable this type of chain operation only during the testing operation. At that time, I need one shift. So I will be shifting this flip-flop output and observing at the final output value. That time I need only one shift in this one clock cycle. But because both the frequencies are different, there may be chances of like two shifts. That time I can add this latch here to lock it, and in the next clock cycle I can shift. So this is one of the application in the for latches. Any doubts or like something? Yes, latches we will have the race around condition. That's why we will go for flip-flops. Usually in the designs, we will be having flip-flops here and all, like we will have D flip-flop. In counters, we will be having T toggle flip-flop or JK flip-flops. Mostly latch, I don't think so. We will be using for any other like this design. Is this in JK, we will be having this not allowed state as toggle state. That is the reason for the this race conditions. My this one will be my SR latch. So here, then this will be my S bar R bar. Now I will have again another NAND gate, and one of the input I will be tying here. One of the input I will be the circuit, right? JK latch. So when S and R both are say yes, in race condition, like I'm sorry, here say S and R, when both are one, it is not allowed. But here, if I have both S1, Just say I'm enabling it. Okay. If both are 0, it will be 1. This will be 1. And this will be in previous state. So you can see JK Qn plus 1. If you see this truth table, you can see. So if it is 0, 1, we will get the previous state. And then same way, if you have 1, 1, it is 0 or 1, 1, 1. It will be 1, 0. You will get the Qn bar here and here Qn. So we have removed that race not allowed state in the JK latch. And as it is in toggle state, say here, this I'm taking it say as a positive level latch. Here my output is set to say 1. After the delay, that 1 will be applied again, feedback, it will be again toggling. Again I will have a toggle to 1. So it will be toggling in this level. So to remove this race condition only, I need to make this clock this much small. If my clock is only like this much, then I won't be seeing any race condition. Or else I will be going from this latch to a flip-flop. Then in flip-flop, we won't have any race condition. Because it will be sensitive only at this positive edge. Whatever it sees, it will give the output for the whole level. In latches, can you explain the... Yes. We will get the race condition only in the latch, not in the flip-flop. And in JK, due to 1-1 condition, we get race condition. Yes, in JK, we will get race condition when it is 1-1. And in latch, 1-1 condition is not allowed. Then why we are getting race condition? No, 1-1 is not allowed in the SR. But JK 1-1 is allowed. 1-1 we will get a toggle. If it is sensitive to the level. If I convert this and make it sensitive to only edge by using say master and slave, that time it will deduct and give me output at the edge. It will retain the value. So in flip flop we will have no race condition. First we started with SR. We saw that 1-1 is having not allowed state. So we modified it and we came to JK. We are in latch only. In JK latch, we made that 1-1 state to toggle. Because it was toggling, we got the race condition. So to remove this, if we go to JK flip-flop, we won't be having this race condition. Any doubts? I am working in VLSI testing and yes, I am currently doing PhD in VLSI testing in IIT Tirupati. My research topic is on VLSI testing. Yes, that is your question, right? Yes. Any other doubts? Okay, first question is where to test this Verilog code. So, yes, in the previous lectures, in the previous week, maybe if you have seen, this is the EDA playground where we can test this Verilog, like simulate this Verilog course. This is an online platform and free platform. So if I like, okay, Prof alone, if I just simulate and show you, you can, okay, this one. Here you go to tools, you can set any one tool, and if you want waveform, you can set EP waveform. And then you can see I have given this dollar monitor, everything I have displayed. So you will be able to see the final output here. So if you can see, if D is 0, the final output is 0, but that 0 is appeared after 1 clock cycle. My clock is 2. For 2 units of time it will be 0. After that 2 units of time it will be 1. Then same way I am giving D as 1 after, and you can see the 1. Even after 10 units. We have to learn after that Verilog and system to learn verification methodology compulsory. If you are like trying for any verification companies, then you have to learn the verification methodologies. For designing, we need a Verilog. Say like if we are trying to design a Mac unit, then Verilog is sufficient. We can write the code. We can simulate it in the EDA playground or any. This is an open source online platform, and for synthesis you can use Cadence, Genus, or Intuit. Then further you can have the steps. For verification methodology, it is verification is another domain. So for that you need to learn. For designing Verilog and yes, for designing Verilog is enough. Verilog and system Verilog is enough. If see, like if you see this RISC-V processor, they are using some coding like Chisel. It's also one of the hardware language. So Verilog is sufficient. So this is one of the coding language, which is like it's an open source hardware descriptive language. But if you learn Verilog, then designing is like you can design any module. Chisel are little high level language, so if you want to design like processor, this will be little bit easier in designing. But if you know Verilog, you can learn any other language easily. This is, I think, one of the recent open source like this. There are many, and difference between analog system and digital system design. Analog system design, you will be learning the like operational amplifier, ADCs. In digital system, we will not be having that intermediate voltage level. We will be having only logic 0 and logic 1. All the combination sequential circuits. The code you showed is like behavioral level. Can we simulate gate level code also in that tool? Yes, you can simulate gate level also. I think this is gate level code only. I have instantiated, this is test bench, but test bench you have to write for every code. You have to pass the values, input values, and you can display the values. The code, main design code is actually gate level only. Okay. Any further doubts? Can we complete? No. If no doubts, then like we can end today's section.
Okay, ma'am. Thank you.
Yes, thank you very much.